Okay, I want to clarify this little stuff that I had a confusion on last week. In particular, this little stuff that I'm talking about is the derivative of the vector p2 in this diagram that goes from O2 to B. So, in this mechanism that we see here, we have, let's suppose our loop goes from point O1 to point O2 to point B to point O1 back. Okay, so I named some vectors, particularly P0 goes from O1 to O2, P2 goes from O2 to B, and P1 goes from B to O1. So this is the first link, this is the second link, this is the third link, remember that. So what we had was that the axes were assigned something like this. We had x naught, y naught. We had some, I don't know, where was x naught, y naught actually in class? I can't exactly remember. Maybe over here, doesn't matter though. X naught, y naught. Let's say x1, x1, y1, x2, y2, and x3, y3. Okay, so we have this loop equation that goes from O1 to O2, P0, plus O2 to B, P2, plus B to O1, P1, equals 0. All right, so we start from O1, came back to O1, so the loop equation must, the vectors must sum to 0. Okay, so then you can write this in coordinates and write this guy in coordinates and come up with the position level loop equations and solve for them, of course. I'm not going to go into that. We've gone into that in class. What I'm going to do immediately is derive the velocity level loop equations. For that, I'm going to differentiate star in time in the 0th frame. So let's go over it again. ddt in 0, p0 plus p1 plus p2 equals 0. And from here I have ddt of p0 in the frame 0 is 0 because the vector p0 is a fixed vector in the 0th frame. So what I'm going to do is I'm going to have ddt in 0 of p1 plus ddt in 0 of p2 equals 0. If you remember, we split this into two, said that we're going to take the derivative of p1 in the first frame, use the differentiation of two frames formula here, remember that, angular velocity 1 and 0 cross p1, and then we took the derivative of vector p2 in the third frame using the differentiation in two frames formula, and we got this equation. And since derivative of p1 in frame 1 is 0, because the vector p1 is fixed in 1, we're left with these three terms here. And in particular, I want to divert our attention, or concentrate our attention on this term here. Okay, so let's look at that term. So we went through with this analysis in class, and it's not the important bit right now. What I'm going to do is concentrate on this term instead. ddt in 3 of p2. I claim that this is equal to ddt in 2 of p2. Can you guess why? If you want to, think about, or not guess actually, can you, discover why. If you want to discover it yourself, pause the video just a little bit, try it yourself, and then come back. Okay. So the way to find this is as follows. So I'm going to use differentiation on two frames formula with A equals the third frame and B equals the second frame. You remember that formula? The general formula that I've written on the board, or we discussed in class, and actually is given in the lecture slides, is something like this. Let me refresh our memories. Differentiation in two frames. The formula was, if you want to take the derivative of any vector in a frame A, this can be equivalently written as the derivative of the same vector in some different frame, B, can be any frame, right? But we have to correct for the mistake that we are doing, and that correction factor is given by angular velocity of B in A cross the same vector V. Okay, that's the formula. So what I'm going to do here is I'm going to start with the derivative of P2 in the second frame. I'm going to start with the derivative of P2 in the third frame. 3 is my A in the differentiation in two frames formula, and express it as a derivative of the same vector in 2. What do I have to add? My correction factor is the angular velocity of frame 2 in frame 3 cross the same vector P2. But notice the diagram. Notice the diagram. These second and third frame, they're always parallel to each other. The axes of the second and third frames are always parallel to each other. X2 is always parallel to X3. Y2 is always parallel to Y3. Indeed, the third body, rigid body, the slider, is actually rotating on the second body. Is actually sliding on the second body, which means that the rotation of the second rigid body and the third rigid body are exactly the same with respect to the inertial frame, right? So what that means is that this angular velocity term, angular velocity of 2 and 3, is going to be 0. You can actually calculate that. What's the rotation matrix between 2 and 3? It's the identity matrix, right? Remember, the rotation matrix from the third frame to the second frame, right? Or the rotation of the second frame with respect to the third frame is the identity matrix. So if I use my definition of angular velocity, what would that be? The skew symmetric matrix that corresponds to the angular velocity would be given by R32 dot, R32 transpose. But R32 dot is 0 because R32 is always the identity matrix, and identity matrix is a constant matrix. The derivative of a constant matrix is 0, which means the angular velocity of 2 and 3 is 0. Yeah? But if that term is 0, then what we have is ddt in 3 of P2 is equal to ddt in 2 of P2. Okay? So that's the first thing. Now, what I started to do in class was I put a point B2 I start with points. So what we said was consider points B2 and B3, right? Coincident with the point B. But the caveat, or the important bit, is that B2 is going to be fixed, is going to be a fixed point on the second rigid body, or the second frame, right? And B3 is going to be a point that's fixed on the slider, or on the third rigid body. But at the current instant of consideration, right, they are coincident. They are exactly on top of each other. Okay. So what I can do then is I can decompose the vector P2 to be a vector that goes from O2 to B2, right? O2 to B2, but remember B2 is fixed on 2, plus a vector that goes from B2 to B3. Okay? Now, what I have is a derivative of this vector p2 in the third frame in my equations. In my derivative, in my kinematics equations, I have the derivative of p2 in the third frame. Okay, so let me work on that a little bit, massage it a little bit. I found out here that the derivative of p2 in the third frame was equal to the of its derivative in the second frame, right? So I can write d dt in 2 of p2. Now I'm going to use this decomposition of p2, okay? So it's going to be d dt in 2 of po2 b2 plus p b2 b3, right? But and then let me distribute this. So let me distribute that. d dt in 2 of po2 b2 plus d dt into of position vector from b2 to b3, right? But notice that the position vector that goes from O2 here to B2, remember B2 is fixed on 2, is fixed. Both point O2 and both point B2 are fixed on the second frame, right? So which means that the derivative of that position vector that goes from O2 to B2 is 0. Yeah? So now I'm left with d dt in 3 of P2 is equal to d dt in 2 of the vector that goes from B2 to B3. But what is this? This is the derivative of a position vector that goes from a point fixed in the second frame, right, to a point B3 that's moving in the second frame, and this derivative is taken in the second frame. The second frame, remember, is again the frame that this point is fixed in. This is literally the definition of the velocity of the point B3 in the second frame, okay? So this is, long story short, this is what I got confused in class with. Essentially, what I forgot to do first is this derivation. If I did that derivation first, I wouldn't have been confused. But anyway, now we can use this idea, right? That the derivative of the vector p2 in the third frame is equal to the velocity of the point b3 in the second frame, right? So I can go ahead and insert this calculation over here in the velocity level velocity level loop equations. So let me move that all the way over here and keep on working on it. What that now looks like is angular velocity of 1 and 0 cross p1 plus velocity of point b3 in 2 plus angular velocity of 3 in 0 cross p2 equals 0. Okay, so this is the velocity level equations in vector form. Haven't been expressed in any coordinate system anymore, right? Yeah, just yet, I should say. So notice that velocity of b3 in the second frame actually looks like d3 dot in the x2 direction. Yeah. So because this is exactly equal to the derivative of the vector p2 in the second frame and the vector p2 in the second vector p2, the vector p2 is indeed equal to d3x2, and then this is equal to d3x2. So these two match. Well, so just to finish up this video, I'm just going to take the Doublestory equations and take another derivative to do to derive the acceleration level equations. Yeah. So what do I need to do? I need to take another derivative in the zeroth frame of this whole equation. Of course, now some of the derivatives I will have already done, So I can go back and inspect my velocity level analysis and just copy my answers from there. So let me distribute the derivative on each term here. That's the starting point. Now I'm using the Leibniz rule, or the product rule of differentiation here, to differentiate the cross product. Now this is the derivative of the vector p1 in the zeroth frame, and we have already done that in the velocity level analysis. I can just copy my stuff from earlier. This one here, look at this. This one here is a derivative of the velocity of the point p3 in the second frame. What I should do here is use differentiation in two frames formula to differentiate this thing in the second frame, because I know that this term is going to be the acceleration of point p3 in the second frame. Yeah, but I have to add my correction term, remember. And then again use the product rule of differentiation, and then differentiate in 0 the vector p2. Remember, we've just done it over here. This is the derivative, right? Sorry, here we did the derivative, so I can just copy my results from earlier. Okay, so this is going to look like angular velocity of 1 and 0 cross p1 plus angular velocity, this is the angular acceleration, I'm sorry, angular acceleration of 1 and 0 cross p1 plus angular velocity of 1 and 0 cross angular velocity of 1 and 0 cross p1. This was our earlier result, that the derivative of vector p1 in the zeroth frame was equal to the angular velocity of 1 and 0 cross p1. Yeah. Plus, now this is the definition of the acceleration of the point p3. This is the acceleration of point p3 in the frame 2 plus angular velocity of 2 in 0 cross velocity of point p3 in 2 plus angular acceleration of 3 in 0 cross p2 plus angular velocity of 3 in 0 cross ddt of p2 in 0. What did that entail? Well, that was exactly this whole term here. Sorry, this guy was, remember, this was exactly equal to ddt in 0 of the vector p2. Yeah, so I can just copy that part down here. This is going to be velocity of p3 in 2 plus angular velocity of 3 in 0 cross p2 equals 0. Yeah, and finally, let me collect some terms together. I have the acceleration of point p3 in 2 plus, so look at this term here and then look at this term here. Those two terms are exactly the same terms, so I can create, I can just add them together and make them 2 angular velocity of 3 in 0 cross velocity of p3 in 2. Yeah, remember, this was the Coriolis acceleration, the one that I've just written. Plus, what do we have? We have angular velocity of 1 and 0 cross angular velocity of 1 and 0 cross p1 plus let me actually, just bear with me just a second. Let me write this over here. Angular velocity of 1 and 0 cross angular velocity of 1 and 0 cross p1 plus angular velocity of 3 and 0 cross angular velocity of 3 and 0 cross p2. These two terms that I've written, these are both centripetal accelerations, and then plus we have angular acceleration of 1 and 0 cross p1 plus angular acceleration of 3 and 0 cross P2. This whole thing is equal to 0. Okay? And these are the acceleration level loop equations, which will then have to be expressed in a common frame and added together to form the acceleration level scalar equations, from which you would solve for the unknowns. In this case, the unknowns would be theta2 double dot and what? Theta2 double dot and d3 double dot. Those would be the unknowns in this case. Okay, I'll end the video here. Thank you.